I'm Frederick C. Hila, and I would like to discuss our topic on the synthesis and irradiation with high energy electrons of the material known as alumina. Alumina or aluminum oxide is a very important material because it has high mechanical, thermal, and chemical properties. Because of this, it is a candidate material for use in high energy radiation. The effect of radiation to the alumina is very important to study because radiation has many effects on materials. The common ways of producing alumina is through the bare process, but it demands high energy. Therefore, many studies have used waste aluminum cans to produce pure alumina. Therefore, the objective of this study is to synthesize alumina using low energy method and to see the effects of high energy electron radiation. In the synthesis of our alumina, we used sol-gel method with the reactions described below. In order for us to study the effect of electron radiation, we created two pellets when one is the regular and one is the irradiated by electron beam. The irradiation was made in the Philippine Nuclear Research Institute's Linear Accelerator Facility. For our results, we used XRD and PGA-DTA to validate if we had indeed synthesized the alumina using the sol-gel method. The results of the SEM for the regular pellet is shown in the left, and for the E-beam irradiated pellet shown in the right. There is a difference between the two, where the irradiated pellet has larger grain sizes. This corresponds to changes in the morphology within the pellet.
Hi, I am Ismeria, one of the co-authors to present this paper on nanoscale contact charging of molybdenum disulfide by atomic force microscope. We took interest in molybdenum disulfide because of TENGs. TENGs, or triboelectric nanogenerators, can convert mechanical energy into electrical energy by means of contact, rubbing, or bending. These are low-cost materials that do not need external source. Molybdenum disulfide is a promising material for TENGs. These are 2D and part of TMD class materials which can be fabricated into thin sheets. It is stackable, such that it's a good candidate for medical biosensors. Also, there are very few studies of pure bulk MOS2 contact electrification, especially at nanoscale level. In our experiment, we use an AFM with Kelvin probe options for both surface and potential topography. A tapping mode, which has a frequency of 300 kHz and a bias voltage which varies from 0 to ±2 volts is applied to the tip. The red box magnified shows the tip contacts the surface repeatedly at high frequency. The DC bias influences the outcome of the MOS2 surface. Positive bias generates more negative on the surface. A negative bias generates more positive on the surface. Also, upon separation, some charges may back tunnel due to the electric field created between the two surfaces. In effect, you create a bipolar surface. In conclusion, the bipolar charging of the surface of molybdenum disulfide can be tuned to the desired charge affinity by applying bias voltage on the CE applicator. A promising future for TENG devices. Thank you.
Plasma treatment of monomers is a method of initiating polymerization and producing films with different surface characteristics. The advantages over conventional polymerization include the use of less chemicals, making it more energy and cost-effective. One disadvantage, however, is the necessity of a plasma source, which normally consumes large amounts of space, energy, and time. The atmospheric pressure plasma jet, or APPJ, does not require a vacuum system to produce plasma, making it a quick and convenient method in treating monomers. Previous research by Tan et al. Has shown the plasma polymerization of styrene into polystyrene with the APPJ, and the treatment of metal metacolate, or MMA, produce films with a change in wettability relative to the untreated films. This research aims to treat MMA and styrene under the APPJ and optimize varying discharge parameters, namely gas, method, treatment time, and substrate to change the wettability of the coated surface. MMA was treated first in bulk, then dropped immediately onto the substrate in triplicate trials. The wettability was measured through the static sessile drop method. Bulk treatment resulted in white polymethyl methacrylate powders with enhanced hydrophilicity, especially with the incorporation of higher power nitrogen plasma and longer treatment times. Styrene, bulk treated the same way and dropped on glass, displayed contact angles similar to that of untreated styrene. However, only styrene treated with nitrogen plasma produced a hydrophobic coating. For drop treatment, styrene was first dropped on a glass substrate using a dropper and then immediately treated under the APPJ, while for spray treatment, styrene was sprayed twice using a glass atomizer, then immediately plasma treated. These did not show a drastic change in wettability but produced films with different surface characteristics. The plasma treatment of metal methacrylate and styrene under the APPJ produced apparent physicochemical changes in the monomers and changed the wettability of the coated surface.
Good day, everyone. Our case study is entitled Monte Carlo simulation of cobalt-60 ion irradiation into SiC-MOSFET. MOSFET is commonly used in amplification and switching of electronic signal of devices, and polysilicon is widely used as a gate in this transistor. It has been a replacement for aluminum that melts in high temperature. However, polysilicon is facing a depletion issue that may result to unwanted and unpredicted behavior along the circuitry. In addressing this issue, we simulated refractory metals such as molybdenum and tantalum. In doing so, we utilized stopping and range of ion matter software in calculating the nuclear and electronic stopping to determine the energy loss of cobalt-60 and the damage to induce to the material. So 3 types of gate were being simulated: the polysilicon, molybdenum, and tantalum. However, the polysilicon will only serve as basis in concluding which refractory metal between the two has a more efficient result that can be a replacement for the polysilicon gate. So in this figure 8, we can observe that the path incident is more likely to travel a straight path, the higher the energy levels, and in this scope, quantum scattering takes place. So these are the tabulated results of simulation in each energy level: 1 MeV, 5 MeV, and 10 MeV. Polysilicon exhibits a good result, having a less damage and vacancy due to high energy absorbed during collision and followed by molybdenum. This absorbed energy implies that there is a higher number of inelastic collision than elastic one and resulted to less vacancy. So the simulation allowed us to conclude that between tantalum and molybdenum, the latter is more efficient as a replacement for the polysilicon gate. Molybdenum may fill in the depletion issue of polysilicon gate and become a better metal gate that would make our devices in good service. So these are the references in conducting the study. Thank you.
My name is Joseph A. De Mesa, and on behalf of my co-authors, I will be presenting our work on numerical investigation of laser processing of silicon. Laser material processing is the modification of the material surface using an intense laser. LNP can modify materials with high accuracy and precision that is appealing to a lot of applications like cutting, marking, and even film deposition. However, LNP is still not fully understood to a wide laser matter combination. So it's important to study well the laser matter interaction process, especially the energy absorbed in different materials. Our group aims to develop a numerical code that will describe this process through ultrafast laser processing of silicon. We added a carrier generation equation to extend the two-temperature model that is only conventionally used for metals. We first simulate the LNP using a single pulse and compare it with related literatures. Then we continue the simulation to multi-pulse case. We choose the laser specs that are close to our experimental parameters. We intend to elucidate what ablation mechanism dominates at these laser parameters. Our results showed how the electron and lattice temperature evolved with time for different laser fluents. We can define fluence threshold in non-thermal ablation by just looking at the lattice temperature and carrier density. This is in good agreement with experimental results of Allen Spatcher. For multi-pulse case, our simulation showed how the lattice temperature continuously increases with number of pulses. This suggests that even at low fluence, heat accumulation can induce laser damage for high repetition pulse laser. This could be the reason why we can ablate and deposit film of cerium oxide even at low laser fluence. The simulation can be extended to other semiconductor material. For more questions, you can reach me using my email below or use the QR code to direct you to our research paper. Thank you.
I'm here to report the surface modification of water hyacinth fiber with ethanol pretreatment in argon plasma treatment. Water hyacinth has been the main problem in terms of marine transportation, fishing, and irrigation schemes, environmental awareness, and increasingly concerned with sustainable development, including substitute to non-renewable materials. This study aims to modify the surface of water hyacinth fiber using argon plasma treatment. For our methodology, the water hyacinth fiber samples were provided by the PTRI, while ethanol was provided by the PUP Manila. For the pretreatment procedure, the water hyacinth fibers were divided into 4 groups: control or untreated, ethanol pretreated only, plasma treated only, and ethanol pretreated for 10 minutes, followed by argon plasma treatment. The surface property of the water hyacinth fibers, such as contact angle and surface free energy, were investigated using the sessile drop technique. As the results, polar liquids such as water, the contact angle decreases considerably after exposure to plasma treatment. Ethanol introduces a polar atom on the surface of the fiber, which increases its surface adhesion. Since ethanol is apolar in nature, the surface interacts with the said substance are predominantly polar and considered as hydrophilic. The total surface free energy values of water hyacinth fiber are observed to increase except for plasma treated and plasma untreated for 3 minutes, as shown on the graph. We concluded that after treatment, contact angle values of water hyacinth fiber in water decreases considerably and display an improved wettability, while for the glycerin is due to the formation of hydrophilic groups. Thank you for attending this conference, and this presentation would not reach a success without the help and guidance of SPP and Mr. Rogelio Dizon. If you have any inquiries, you could contact us in the codes that are shown below. Have a nice day.
Thin films are used in a wide range of applications, such as integrated circuits, solar cells, protective coatings for optical instruments, and medical implants. With this versatile potential in mind, how can we integrate thin film technology in an undergraduate laboratory course where students can understand the fabrication and characterization of thin films? Hello, I am Alvaro Abesa, presenting our study on optical transmission spectroscopy of aluminum thin films deposited on glass substrates via thermal evaporation. One way to create a thin film is by applying a current through a source material, in our case aluminum, heating this material until it evaporates and deposits on a substrate. This was done in a high vacuum to prevent oxidation and to lower the vapor temperature of aluminum. We performed 4 depositions with varying deposition times. These films were then transferred to an optical transmission setup, where a halogen lamp was directed to the sample and the transmitted light was collected by an optic fiber connected to a spectrometer. The transmission spectrum was measured at different points of the grown aluminum films. Transmittance was then calculated by dividing the transmission spectrum of the sample by the emission spectrum of the incident light. Comparing the transmittance spectra of the 4 grown films, a trend can be observed. An increased deposition time generally means a decrease in transmittance, implying that more aluminum atoms were able to evaporate and deposit onto the substrate. This was the case for all points tested on the films, whether at the center, the left, or the right. These results suggest that the simplicity of the deposition setup and the characterization used in this study makes the experiment viable for integration in an undergraduate laboratory course as a stepping stone in thin film research. For more information, scan the QR code on your screen, which will lead to our full manuscript.
Good day, everyone. From the National Institute of Physics, I'm Bianica Tinte presenting our work on the laser ablation of cerium oxide with different target scanning speeds. Pulse laser ablation is a material removal technique involving high-fluence laser pulses. The study of laser-material interaction during this process allows us to better form nanoparticles for their collection, study laser-induced plasma for thin film deposition, and realize the ablation mechanisms for optimal surface structuring. In this study, we ablated a cerium oxide pellet with a titanium sapphire laser in vacuum pressure. The target holder was driven by a stepper motor that rotates at a different speed during the ablation of a defined radius. This produced the following grooves whose surface morphology was characterized with a surface electron microscope. For a slower scanning speed, pulses arrive at almost the same point on the target surface. This promotes heat accumulation for a more efficient ablation seen from the mechanical damage here. And that also widens the heat-affected zone, so our grooves are wider as well. At faster target rotations, the heated region from each pulse is more spatially displaced from the previous. Thus, there is less surface temperature achieved. So instead of ablating an entire area like this, only the central part of the heat-affected zone may reach the threshold temperature for ablation. The rest, especially the edges, will only experience onset ablation, or melting. This is seen in the fluid-like interfaces, the narrower grooves, and the seemingly smoother groove surfaces. There is much to be done to improve this study, such as measuring the laser spot size relative to the crater width, quantifying the depth and smoothness of the grooves, and extending research to different ablation media and more target scanning speeds. Once again, I'm Biani Catinte, and thank you for your attention.